So now let's look at the different parameters that we can play with when we're building our convolutional neural networks. So one of the more important ones is the size of the kernel. And the kernel, we say kernel, but we can also say filter. So typically we denote this as f, and it's usually a square. So when we say f equals 3, we usually mean a kernel that's a 3 by 3. If we say f equals 5, we usually mean a kernel that's 5 by 5. And again, depending on the size of the kernel that you're going to use, well, this might mean more parameters to your network, but it might also mean that the kernel can look at more neighbors when making its decisions. So this is an architectural decision that you're going to have to make. And later on today, we're going to look at different architectures and why they choose to use the parameters that they use. So another important parameter that we can tweak is the stride. So the stride, again, we denote this as S, usually represents the number of pixels to move in X and Y when we're displacing our kernel, when we do the operations in our convolution. So typically, we usually see values of stride of 1 or 2. And so for a stride of 1, that's what we've been seeing so far. We take our kernel, and we displace it by 1 pixel in X. And then once we finish all across X, we displace it by one pixel in Y. And we displace ourselves along Y until we've gone through our whole image. When we have a stride of 2, well, we take a step of 2 in each direction. So here I have some animations for both stride in 1 and stride 2. So you can see that stride 2 is obviously going to move faster, but a stride of 2 will have a smaller output map. So again, this is a design decision that you have to make when you're building your different architectures, and we're going to look at different examples where both are used later on today. So here, I'm going to show you the specific example of stride equals 2. So you can see here with the stride of 2, the feature map is much smaller than the input. So obviously, this goes into the decision, do you want to be reducing your feature map when you're defining your stride? Now let's look a bit at some 2D convolution arithmetic. So how do we figure out the dimensions of our output with respect to our input based on the parameters that we just saw? So there are some equations that are relatively straightforward that will relate the width and height of an output with respect to its input. So in general, if we have Wn by Hn, so width and a height of our input, we can figure out the width and height of our output by plugging in all of these numbers. So here we have in this example, so we have our kernel that has a 3 by 3. We're using a stride of 1. We have our width and our height that are equal to 6, right? So that's the number of pixels for each. So if we plug in the numbers, we see that our W out and H out, in this case because of the symmetry of the problem, is equal to 4, which is exactly what we'd expect. So you may have noticed up until now that the output is getting smaller than the input. That's not always practical. So there's a trick that we can use, and that's often used in literature, which is called padding. And padding uses some kind of strategy to pad the borders such that your input is now artificially larger, and even though your output is smaller than your input, with respect to your original input, it might be a different size. So the number of pixels that we use to pad is denoted as p, and we're going to look at some different padding strategies. But first, let's look at an animation of what that means. So suppose I have a gray border. Now I can do my convolution just like I was doing it before, but now my feature map or my output is the exact same size as my input. So again, you could imagine if you're building a very deep convolutional neural network, it can be useful to preserve the spatial extent of your features, because if as you go deeper, your outputs get smaller and smaller, there's going to be inherently a limit to how deep you can go. So if we denote p as the number of pixels with which we pad our borders, again, we can do the same kind of arithmetic. So we just add a term here that represents the padding. And again, plugging in the numbers for our same example, Wn, Hn is equal to 6. We still have our stride of 1, our padding of 1, our kernel size of 3, and we get that our W out is equal to H out, which is equal to 6. And again, I'll let you go home and do the math and look this over, but these equations should start making sense once you do that. So there are 3 ways that we can do our padding. And again, typically when you look at PyTorch or TensorFlow, there are really three ways that you could specify how to do this padding. There are the defaults. So we're going to look at the three main ways that are typically implemented. The first one is what's called a valid convolution. So you do enough padding to make sure that your convolution is valid. In this case, what that means is the kernel is allowed to visit only positions where the kernel is fully contained within the image. So really, we can translate this as no padding whatsoever. So when you're implementing your convolution, you have a padding parameter, and you can set it as valid, and usually that will mean that no padding will happen. So the next kind of padding that we can have is what's called the same convolution. So this is what we saw earlier. We add just enough padding to make sure that the output size of our feature map is exactly the same as our input size. So again, this is very useful in the context of building deep networks, and we're going to look at some networks that exploit that later today. This one is a bit trickier in terms of the wording. So this is the full convolution. And in the case of the full convolution, what you want to do is you just want to make sure that every pixel is visited just as many times. So you don't want a border pixel to be visited less times by your kernel just because it's on the border. So you add a bit more padding. And here you'll notice in this specific example that every pixel is visited 3 times, which is the size of our kernel. Right? So it's the wording is a little bit trickier, but really in the end, we just want to make sure that every pixel contributes equally to the output signal. This comes with a certain trade-off because we have to add more padding for that. Now let's talk about padding strategies. So what do we do to actually pad these borders? The most common strategy that's used, I would say almost everywhere, is what's called zero padding. So when we have zero padding, we take our input, which might be some kind of matrix, and we simply add zeros around it. So here's an example of declaring zero padding in TensorFlow, and you just add zeros everywhere around your input. And again, this is typically what's used with padding. You can set the constant to be whatever you want. It doesn't have to be 0, but in general, 0 is what's used. Now we have some other strategies for padding, and again, this might depend on the kind of images that you're dealing with or the kind of inputs that you're dealing with. It might make more sense in the context of your use case to be using a different kind of padding. So here we have this reflect padding, which is a bit more subtle. So what we do is we take a pixel and we reflect what it sees on its diagonals. So here, for example, we have the 3, we have a 5 and a 7, and we reflect that back on this 5 and 7. And I encourage you to go play around with these different paddings and go see for yourself sort of what different sizes might do and how these have been implemented. Another one is symmetric, so very similar to the reflect padding, except that it's symmetric with respect to a hinge point on these borders. So here you see we have our 3, 5, and now we're symmetric with respect to this point. We have our 3, 5. Similarly here we have 3, 6 and 3, 6, etc. So again, take your time to go home and read these. Go read the documentation when you use these different paddings. But typically, more often than not, the zero padding is the padding of choice for most architectures. So now let's talk of depth. So far, we've seen that by using one kernel and one feature map, we get one output. However, we might want to have more outputs. So how do we get more outputs? How do we get a volume out of our convolution? Well, we simply use more kernels. And that's the idea behind convolutional neural networks. We use many, many kernels on the same inputs to be able to learn many different features of a same input. So the depth is typically denoted as D. And this will represent the volume, essentially, of your output. And we also talk about this as being the number of channels. So it can be kind of used interchangeably, the depth or the number of channels. And in fact, in PyTorch and TensorFlow, it's usually referred to as the number of channels for the depth of your tensor. And the resulting feature maps are stacked to produce a volume. Okay, so let's look at an animation of what this means. So here we use a stride of 1, sort of what we've seen before. So we do our first convolution. Now we use another kernel. We have a second convolution happening on top. Another kernel. We continue stacking and stacking and stacking. And we can define this as a user, the depth of our network. How many kernels do we want to be acting on this one input and get a resulting volume as an output? And again, this will be an architectural decision. And of course, the more kernels you use, the more parameters you have to your network, the more you have to learn. So another term that was a little bit overlooked in terms of the animation is the bias. So just like in multi-layer perceptrons, we have to add a constant bias B to every depth of the layer in our network. So we do these convolutions, and this is another learnable parameter. The network will figure out which bias to add to sort of offset the output feature maps based on what the network decides is best for the specific task at hand. And again, if you look at the matrix multiplication in the case of MLPs, it's very analogous to the CNN convolution. The only difference really is the operation that we're using. So now let's look at pooling. So pooling is a very popular technique used to downsample images. Pooling is one of those things that was inherently empirical but was shown to work really well. So pooling, again, will really be useful in the context of taking an image or taking an input and reducing its size significantly and cheaply. A very popular kind of pooling is what's called max pooling. And so in the case of max pooling, what we do is we have our input, so for example, some image, and we take the equivalent of what's a kernel, and so let's say that we take a 2x2 kernel. And what we're going to do is we're going to take this 2x2 kernel, we're going to place it over 4 squares, 4 pixels of our image, and we're going to select for the maximum value. So here, if we place our 2x2 kernel over here and we select the maximum value, we see that this maximum value is 6. So we take that 6 and we place it over here. We then move over with stride 2. Again, this is a very typical thing to find when we use max pooling, is a 2x2 filter and a stride of 2. So we move over 2 pixels, we place our 2x2 kernel here, and we select the maximum value. So here, our maximum value is of 8. And we continue doing this for the whole image. And what this does is it gives us an output or a feature map that's exactly half the size of the input. So again, this is very useful in the context of, say we're trying to classify a dog. If we do this max pooling, it's a very cheap operation. And then we can get a 128 by 128 representation, so we don't have to necessarily use more kernels. So this can be very useful in the context where if we know that reducing our image won't change too much, we reduce our image, and then what we have to learn will be, the parameters that we have to learn will be a lot less. So let's look at an animation. So here again we have our kernel, and we select the maximum value at every point. And again, this maximum value could sort of be anywhere, right? It's really just an operation that says pick the max value. And you can have also minimum value pooling. You can have average value pooling. There are different kinds of pooling, but typically in literature and most architectures, the max pooling is the one that's used. And the kind of rationale behind it is that it's going to avoid the case where the network focuses on some very fine details. So if we're max pooling, if we're reducing our image by a size of 2, we still typically want the convolutional neural network to focus on more or less the same details, specifically in tasks like classification. And again, it reduces by a factor of 2 in every dimension. And you can imagine that you could play with the size of the kernel, and you can play with the stride to get different dimensions. But again, in literature, typically we see a 2x2 max pooling with stride 2. So another way to downsample our input is by using something called dilated convolutions. They're also called Atris convolutions. And the reason why they're called Atris convolutions is kind of funny. They were first proposed by French authors, and so they called them convolutions à trous, right, holes. And this was translated as Atris convolutions. So I believe in Keras, if you look at the documentation, they're called Atris convolutions. It's the same thing as dilated convolution. So in a case of a dilated convolution, it's the same kind of operation in our convolution, but here we have a factor D that determines the pixel spacing between our kernels. So we have our yellow kernel here, but now we have a spacing of 1 between the kernels. So again, this allows us to still have our 3x3 kernel, but instead of visiting only local patches, we might visit patches that are further away. And this, again, depends on the use case of what you're doing. If you think that it's more important for your kernels to be focusing both on local and features that are a bit further away, then dilated convolutions can be very useful in your use case. However, dilated convolutions will also downsample your output. Finally, we have the transposed convolutions. So the transpose convolution is a bit trickier. It's a bit different from the original convolution definition. We're not going to go too much into detail right now as to what transpose convolution is, but really what you should remember is that they're used to increase the resolution of a feature map. So usually, we're going to see this later today. If you're doing the task of classification, you take your image and you want to reduce it to just a few numbers. But we'll see, again later throughout this day, that there might be other tasks that you might want your network to do that will restore your original image. So you'll need some kind of operation to increase the resolution. And the transpose convolutions can be used for that. The math is slightly different than the typical convolutions we saw, and we're going to look at what that means later on today, how the math is different. But I put a link here that's really good at explaining this, so if you're curious, you can go and read up on it. But again, we're going to look at this definition a bit more formally later today.